Throughout 2006-2007, Titan engineers faced a challenge. The well-designed preheater tower and large dimensions of the cyclones allowed for an increase in overall clinker production. The challenge ahead was to make the modifications necessary to accommodate this increase while at the same time to improve the overall efficiency of the pyro operation. Although the kiln and preheater tower were originally designed and commissioned to produce a capacity of 5,000 short tons of clinker a day, the realization that the preheater tower could accommodate up to 6,000 tons was soon realized. In order to achieve this goal successfully, existing problems in the cooler, the proverbial Achilles tendon to this production increase, had to be dealt with and solved.
Prior to March 2007, limitation in the design of the Control Impact System, or CIS, failed to stabilize the pyro process in the face of changing chemistry. Constant formation of snowmen occurring with alarming frequency were creating havoc on the total operation of the pyro process. With the conversion of the Control Impact System to an Air Blaster Control System, ABC, the constant formation of snowmen was almost eliminated. This brought dramatic improvement to the stability and overall operation of the pyro process.
A snowman is an agglomeration that occurs in the front end of the cooler where the material discharges from the kiln. Over time, these formations build to the point where a restriction of airflow is inevitable. This restriction causes inconsistent airflow, destabilizing both secondary and tertiary air temperatures, resulting in moderate to severe cycling throughout the entire pyro system. The cooler grates in the CIS and crossbars throughout the cooler were failing frequently due to a combination of the formations of these snowmen as well as the high material temperatures exiting the kiln. The grates were simply unable to handle this combination of stress and heat. In a planned shutdown on March of 2007, designs to address and solve these issues were moved from the stages of planning into action. It was during this shutdown that a grating was introduced that could withstand temperatures up to 1,000 degrees Fahrenheit. Redirection of the blaster airflow distributed throughout the grates brought precise air power where and when needed to the troubled areas of the cooler where prior snowmen formations were virtually unreachable under full production.
Before me, I'm looking at two separate grades. This one right here is from the CIS, and this one is the ABC. The difference in both grades is the quality of the metal. This one is a more lighter metal compared to this cast iron. This is designed for a higher temperature, as high as 1,000 degrees, while this one is less than 400 degrees. Notice this one has a section where the clinker is allowed to sit inside here. It's about an inch in depth, and with this clinker, this cool, fresh clinker that is always sitting inside here, it helps as an insulation for the grate with respect to the clinker temperature. Now, the problem we had with this grate, which is the CIS, old system, whenever we build the snowman, consistent blasting create a problem with this layer of clinker that is sitting inside here. It actually is removed by the blasting, and the hotter clinker gets inside the grates and burnt these sections. In contrast, this grate, the ABC grate, was designed for hot clinker, the surface to be attacked by this hot clinker. This layer of clinker is rapidly removed from this ABC inlet by blasts that comes through these holes. These are the blasts from the blasters. These aligned holes allow the clinker to be blasted off the grate plate, thus not allowing this hot clinker to sit here for any length of time so that it might create any damage to the grates itself. it is much more robust, and with this type of step formation, it allows this grate to perform a lot better in comparison to this CIS grate.
Three smaller V-belt driven fans in the back of the cooler were replaced with larger direct drive fans, adding more reliability and helping to cool the exiting temperature more efficiently. The addition of the heat exchangers in the ductwork leading to the vent fan cooled the air temperature by as much as 500 degrees Fahrenheit before reaching the fan. The previous problems of the vent fan going down on high temperature were solved. This also solved the problem of heat rushing to the dust collector inlet, adding additional protection to the dust collector and eliminating the baghouse fan from going down. This alone saves valuable time in restarting the system after an unexpected shutdown. Rather than bleeding the blasters out of air in a single blast, the modifications of the blasters allowed them to discharge only half their load in a single shot, increasing their effectiveness. With all of these changes, the cooler bed spread out more evenly throughout the cooler. The cooler speed could be slowed, adding additional residence time to the clinker. The clinker exit temperature dropped. More consistent secondary and tertiary air temperatures added overall efficiency and achieved far greater stability throughout the entire pyro system. Here, from one of 6 op stations, an operator can select the blasters either individually or by sequence to target a specific area. If you look closely in the left-hand corner, you can see a formation of a snowman. Before the modifications of the ABC system, this might have grown into a significant problem. Watch now as the new ABC system works as designed. This is a large load created after the pan conveyor was stopped for routine maintenance. Watch the new ABC as it effectively breaks up and spreads the load, sending it down the cooler.
CIS was the original system that came with this FLS 5-stage preheater, and we thought that worked very well. But then we were introduced to the air blast compartment system, the ABC, better known as, and since we've been using it since last March, it's almost a 60 to 70% improvement. The ABC compartment, the river of clinker flows much better. The improvements are amazing. The heat exchanger was also improved. That was something we didn't have before. It was troubling how to control as an operator when you have an upset condition, how to control the cooler vent fan and hold its temperature low. And since the heat exchanger has been implemented, it's a new world. It's much better, it's more reliable, and the system as a control room operator is 100% better for me. Now, before, when we had an upset condition, we in the cooler, due to chemistry change or whatever mishaps, you would lose the vent fan on excessive temperature. Since the heat exchanger has been implemented, I have not lost the vent fan at all.
I learned a long time ago that if your cooler's straight, your kiln will follow. This holds true in our plant, in our wet plant, in our dry plant, and any cement plant in America. It's one of those cases where the tail really does wag the dog. And anything you can do to improve the operation of the cooler is definitely a plus and needs to be done. The protection that we now have in place for our baghouse and for our vent fan and our baghouse fan, that kind of protection is just an absolute plus. And you can't really put a price tag on that kind of protection. Therefore, the changes that are made throughout this project, and as I do the film and look over the film, I realize just how much improvement has been done and just how much the overall operation has run so much better. So it's a wonderful thing to be a part of, and I'm just proud of all the people that had the ideas that came up with these and implemented them.
The results of all these changes were nothing short of amazing, with each of these problems being addressed and solved. The production goals were met, and we are on our way to achieving our major objective of 6,000 tons of clinker a day. We at Titan Pennsuco are proud of the challenges we face and the results we have been able to achieve by overcoming these challenges.